Okay, so in this video, we're going to just review some loops and functions so we know what those things are. I'm not going to go into too much detail because that's something you can review elsewhere on the internet. And then we're going to talk about implementation of SuperCollider-style patterns and using the scheduler with async functions to schedule things into the future. So we're going to start by importing the Python library. And here's a for loop for I in range 0 to 10, print I. So notice that it prints 0 to 9. So it prints inclusive of the 0 and exclusive of the 10. So it's not going to print the 10. You can also make it skip by a value. So that goes 0 to 4, 6, 8, and also doesn't include the 10. A while loop is like a for loop, but it has a thing you're going to test in order to continue. So in this case, we have a counter that is 0. While the counter is less than 10, it's going to print the counter and then increment the counter. So that goes from 0 to 9. And the thing I just changed, if we change that to 2, that's going to go from 0 to 4, 6, 8, right? So the counter is 0. Is the counter less than 10? Yes. Print it, add 2. Is it less than 10? Yes. Print it, add 2 until this says false, and then it leaves the while loop. And then functions, and we're going to have a different version of this coming up, but this is a function. It adds 2 values. So def add A and B. So you gets 2 arguments and returns A plus B. So if you define that function and then you call the function with 2 values, it will take A, which is 5, and B, which is 7, and add them together, right? That's just laying the groundwork. If any of that was news to you, check out another video on the internet about it. Okay, so now we're going to look at some SuperCollider-style patterns. SuperCollider has a very robust and developed over decades patterning system, but there's a couple things, and it's, we're not trying to implement that, but there's a couple things that are invaluable, and those are the things I've implemented here. pseek, prand, pxrand, and pvoice allocator, which I'm not going to talk about right now, but that basically is used for polyphonic voice allocation. Pseek, what it does is, so we're going to define it as my sequence is pseek. And we have to give it a list of values. So a list is in brackets, right? And we will give it 2, 3, 5, 7, 11, right? So we define the sequence, and then we say seek.next. And we can run seek.next as many times as we want, and it will keep giving us list of primes up to 11, 2 to 11, right? So that's what a sequence is. Because of the way Python is, we could say define our list algorithmically. So we could make our list, we'll call it maybe notes equals list range 60, 72. So this is going to give us a chromatic list of notes. And if we print notes to the screen, right, 60 to 71, because we made a list from the range 60 to 72. And we could use that as our sequence. Right? And that will give us a chromatic scale between C and B. So the 12 notes of the scale. Okay. We could also, if we wanted to do a whole tone scale, now we have a whole tone scale. Okay. So the other patterns are really similar. So seek. So if we do prand, and we give it notes, then do seek.next. Notice that it's giving us random notes from the sequence. And so it'll just pick random values. That's what prand is doing. Now, something you'll notice is sometimes, there we go, it'll repeat. So 62, 62. If you don't want that, and oftentimes you don't, you can just make a pxrand. And pxrand is just like prand, where it's picking a random value, but it won't repeat the same value. So now, as long as there's not two copies of the same value in the list, it's not comparing that. It just won't pick the same value in the list twice in a row. And this will never repeat a value. So those are really, expressive patterns that we can use in our algorithmic note generation. So p-voice allocator, by the way, if you want to look at the examples, the wavetable example uses the p-voice allocator to allocate voices of a polyphonic synth, so that you can keep adding notes to a chord and not worry about using up the same iteration of the synth. So let's go back here. Yeah, so the scheduler in MMMAudio is the way that we can schedule things into the future. So it's something important to music coding systems, and this goes all the way back to the early 80s when Max Matthews made the first system where you can concurrently schedule notes and have sounds happening in a different audio system. Is we need to be able to schedule things into the future, and we need them to be like in independent threads. So we need different schedulers to be able to be happening at the same time and not fighting each other. And that's basically what the scheduler does. So if we make an instance of the scheduler, that's how we make it. And what it does, notice it says down here, async thread started, is it starts a thread, and inside that thread, it can make asynchronous threads. So anything that you send to the scheduler can happen independently of anything else. Otherwise, in Python, if you try to do this otherwise, it'll do something called blocking, and it'll block things from happening until something else is done. So in order to schedule something, we need to make a function, and that function needs to be not just a normal function, but an async function. So async def loop 1, right? So async def means I'm going to make a function, and it's an asynchronous function. It's a specific function that can be scheduled on an asynchronous thread. Just know that if you're scheduling something in the scheduler, it has to be an async def. That's the most important thing. So in here, I can make a for loop. But something that's new that I can do is I can add a wait. Now, I always forget the syntax. Await async io.sleep. Await async io.sleep. And we need to make it sleep for a certain amount of time. Just so you know, in more recent versions of MMMAudio, we don't need to do that. We can just do that. But this will work for everybody. So, okay, so this is my function, right? So all it's going to do is create a for loop, count to 10, but as it counts, each loop, it's going to pause for a tenth of a second, right? So it's not before when we were printing out the outputs of the for loop, it just does all 10 at once, right? What this does is it schedules them into the future. And in order to do that, we need to make a future. So fut, in Python, it's called a future. Fut equals schedge dot schedge. So the function within the scheduler to schedule something is schedge. And we'll give it loop 1. right? So we're saying that the future is something being scheduled, this loop that's being scheduled into the future. And I did that wrong because I never ran this. Okay, so, right? So now that thing, I can slow that down so it's more obvious what's happening. Notice every time I make a change to the function, I need to recompile it. Right. So that took a second to do all 10 of those things. So another thing we can do, let's add a variable here. I'll give it a default of 10, but that's going to be what I'm going to count to. So if I run this, it's going to look exactly the same. But if we do 1000, it's going to get going and it's going to keep going. So if something gets going and you're like, I want that to stop, why won't it stop? Then you can say fut.cancel, and you can cancel the future, right? As long as you have a pointer to it, as long as you have it as a variable. If you don't have it as a variable, you can't. You can stop all schedules. You can also just close the program and start over, which is often the best move. Okay, so great. So now we've figured out how to schedule something into the future, right? So we're going to use this in a second. Well, let's actually change this here. So rather than counting to a number, we're going to loop over a list of values. So instead of count to, we're going to change this to a list of notes. And rather than going in range notes, we're going to go for note in notes, print note. So the for loop, we can do a for loop over a list, and the list, and we'll get each value from the list and print it out. So rather than saying loop 1000, we're going to say loop 60, 62, 64, 65, 67, right? So the schedule is already going. Change what that is. Run this. Okay, so it scheduled the loops, the notes into the future. If we want this to go on forever, there's a couple things we can do. One thing we can do is we could say while true, and then we need all this to tab in. While true, for note in notes, print note, right? So it'll do the for loop, and then it should jump back around and say, okay, that's still true. Do the for loop, jump back around, right? So this should make that sequence forever. And it does. But let's cancel our future. But maybe a better way to do this is to use a sequence. So if we say seek equals pseek notes, then we don't need this to be a for loop, actually. We just need print seek.next. So we can kind of get rid of our for loop. So this is going to happen the same way. We're going to start the loop. It's going to make a sequence of notes, and then it's going to go into this infinite loop. And it does basically the same thing. So let's stop that. And now we're going to make some real notes. I have a function here, or a MMMAudio structure that all it is an oscillator going through a filter and a messenger, and the messenger is going to give us a frequency. So there is also an envelope. So what happens is there's an oscillator and it's always going, and it has a frequency. We don't hear it because there's an envelope and the envelope is not open. But when we send a new frequency, we update self.freq, and this is notify update. So if we get something, it for one sample gives us a trigger. So this is going to set the new frequency, give us a trigger, and the envelope is going to open because it's going to trigger the envelope. The envelope is pretty simple. It goes from 0 to 1 to 0.5 to 0.5 to 0. So it's a classic ADSR envelope. And the parameter times are pretty short. So it's just going to be like 0.2 of a second long. The oscillator has the frequency, and it is going through a filter. In the end, it gets multiplied by the envelope that's being triggered. So that's why we start and stop hearing it, just because the envelope opens up and closes. So yeah, when we start this program, it shouldn't make any sound. But now if we right, and I'm just setting random values, and it's frequencies, so we're going to have to convert our MIDI notes into frequencies. So let's go up to this scheduler. With scheduler's already started, and we have this loop, and we're scheduling it, and we want to make basically a major scale up from do to sol. So rather than printing, we'll say note equals seek.next, and then Maudio dot send float the string, which is freak, and then the frequency. And this isn't what we have, is not a frequency. We have a MIDI note. So MIDI CPS note. Right, so MIDI CPS convert a MIDI note number to a frequency in hertz, right? So it takes a MIDI note number and converts it to hertz. Okay. Yeah, so that is, basic scheduling and SE style patterns. Obviously, we'll have a more interesting example coming up, but that's the basic stuff.